Okay, so physics 2 problem here. I'm going to just kind of set up the problem with what you would know, like what's given in the question. So you have these 3 charges, Q1, which is minus 3 microcoulombs, Q2, which is plus 3 microcoulombs, and Q3, which is plus 4 microcoulombs. And they're placed on an equilateral triangle, on the vertices of the equilateral triangle. What we want to do, and we know the length being 2 meters, we want to know the magnitude and direction of the net electric force exerted on Q3. So first off, let's talk about an equilateral triangle. That means all the sides are the same. So if from here to here is L2, then here to here is L2, here to here is L2. It also means they have equal side angles. All the angles are the same. And we know a triangle has 180 degrees, so 180 divided by 3 is 60. So they all have an angle of 60 degrees. Now what I'm going to do is I'm going to draw a free body diagram on the Q3 charge here. So we'll do it in, let me make a little more room real quick. I'll do it over here. So this is plus 4 microcoulombs, and it's Q4. Okay, well, if we're going to draw a free body diagram for this, I'm going to do it on the triangle itself. I guess we'll use this blue. The charge from Q1 onto Q3, they're going to attract each other because they're different sides. So that's what we have here. This is the force from 1 onto 3. Now Q2 is the same charge, or not the same charge, but the same sign. So it's going to repel it. And this is the force of 2 onto 3, which has components. It has force 2 onto 3 in the x direction. And it has force 2 onto 3 in the y direction. The magnitude's actually... Sorry about that. Someone knocked on the door. So anyways, the magnitude's over here. And this angle theta, we know that this is 60 degrees here because this is 60 degrees here. So by geometry. Well, okay. Let's start by talking about what actual equations we're going to use. We're going to start by saying that our force that we're interested in is Q times charge 1. Well, it could be any charge. So I'll just say Qn times Q. This should be 3, not 4. 3 divided by the distance between them squared. The n could just be 1 or it could be 2. We're going to look at both of them, so that's why I called it that. I didn't want us to get confused. Okay, so let's look at this. Let's first look in the x direction. So our force in the x direction. What do we have? Well, we have the first force is all in the x direction, so it's just minus k times the magnitude of Q1, Q3, divided by the distance between them squared, which we called L, plus k, the magnitude of Q2, Q3, divided by their distance squared, but we just want the x component, so we'll say cosine of 60 degrees. We're going to do the same thing with the y. Now, the y only has one part, and it's minus k Q2, Q3, divided by L squared times sine of 60 degrees. So the force in the x direction is, let's see, I can factor out k, I'll factor out a minus k, a Q3, and L squared, and I'm left with a positive Q1 minus Q2 cosine of 60. Let's see, 60 is going to be up there, so that'll be 1/2, so 1/2 Q2. And we have all these. And there's really no need to simplify. I guess we could. The force for y is going to be minus k Q2, Q3, over L squared times sine is root 3 over 2. So then we just need to plug these in, and let's see what we get. Let's add a little bit of light. So I didn't want to waste your guys' time while I was chugging in the numbers here. But you should get, for this one, minus 0.0135 newtons. And for the other one, if you plug that in, you should get minus 27 over 2 root 3 millinewtons. So then all we have to do, if we want to find the magnitude of the force, now that we know this, we can say that your force is going to be equal to the square root of fx squared plus fy squared, right? We've done this before. And if you plug this in, you should get 27 millinewtons. And if you want to find the angle theta, remember it's tan inverse of our y component over our x component, which should end up being tan inverse of root 3. And if you plug that in, you should get 60 degrees. But 60 degrees is off of our reference. So 60 degrees plus, we're going to want to flip this by doing 180 degrees, is 240. Okay? And that's because the angle we're getting here is off of our forces here, whatever their components are. That's not necessarily where we want to be. We want to know where our magnitude is. So it's important to know that this is telling us the angle between our two forces. That's not what we want. We want to know the angle, the direction it's going off of our reference here. So to do that, you just add 180. Another way to think about this is just using your tan inverse function in terms of where you're at and the domain of tan inverse. You're going to want to spit it out 180 degrees because of the domain of our function. So that's another way to think of it.